As you are all aware, charged particles move easily along magnetic field lines. And in the magnetosphere, what this means is that if you have a measurement at one point, you're often interested in where that field line ends up if you would follow it to some other location. In particular, if you're interested in magnetosphere-ionospheric coupling, and if you have a measurement in the ionosphere, you'd often like to follow the field line through that point into the outer magnetosphere to see where it leads to. This is a subject I would like to talk about today, and I'll do it by discussing a recent quantitative magnetic field model that Gil Mead and myself have developed. Now, of course, when you're near the Earth, an internal model is usually a good enough approximation. But as you get further out into the magnetosphere, you have to take into account the external currents, and this is what we've been concerned with our model. I'd like to begin by saying just a little bit about the model. What we have done is to represent the disturbance field of these currents in the magnetosphere with a power series expansion, keeping terms through quadratic. Now here I've tried to represent some of this three-dimensional information on a two-dimensional slide, and I'd like to take a minute to explain it here. First, look at the bottom portion of the slide. I've taken constant latitude circles here, projected them out to the equatorial plane along field lines. Of course, a dipole would project out to the equatorial plane as a circle, and when you're in close here, it is almost a circle. And as one goes out further, one sees more and more distortion. The dashed lines here are the constant meridian planes. Of course, a dipole would be radial, and so the curve here is due to the sweeping back of the field lines. Because our model is not really good out into the tail, on the top of the slide, I've projected the field lines onto a plane cutting through the tail at 10 Earth radii behind the Earth. So think of this as just a plane cutting through the tail, 10 Earth radii behind it. And again, one can see where the constant latitude, constant local time surfaces intersect this plane through the tail. Now, I won't say much more about this particular slide, but you see it's useful for taking any low latitude measurement and seeing where the corresponding field line goes to in the equatorial plane. So now I'd like to take some older experimental data you're probably familiar with, low altitude data, and use this type of figure to project it to the equatorial plane and the tail. Some years ago, McDermott and Burroughs looked at trapped particle data on a low altitude satellite and determined a high latitude cutoff for trapped particles. And they suggested that this was due to that the particles were trapped out to the last closed field line. And so here it's of interest to see whether the last closed field line of our model corresponds to what they would determine as the last closed field line. I've taken their outer line, their longitudes, and used my model to project those particular points to the equatorial plane. They are shown as the dashed lines here, and the heavy line here is the last closed field line of the model. So to the extent these dotted lines go out to the solid line, there's good agreement between their data and the model. Let's say this is a convection pattern you've seen a lot of today. I projected the sunward convection region. That's what's shown by the shading here. Both the Hepner's data and the Kaufman-Gurnett picture, which is quite similar. Since I'm running short of time, let me just point out that most of the region outside the plasmapause and inside the magnetopause, of course, is the sunward convection region. We can't really say if the sunward convection, or if the convection is sunward all the way out to the magnetopause or not. I think that's an important question, but it can't be answered by this method. In summary, just let me point out that these models are all static models. However, we know that certainly the real field is not static. So the models are primarily of use in projecting average data. One must always keep in mind that the field is actually very dynamic. I just want to emphasize this point, and because I feel it is very important, and certainly the models cannot take into account the rapid changes that do occur during substorms.